Students, good morning, ma.
Good morning, sir.
Wait,
Good
ma,
morning,
wait
sir.
2 minutes. After joining all the students, we will start our class. Please, ma, all of you join fastly. Voice is audible, students. Okay. Students, whiteboard is visible, ma?
Yes, sir.
Okay, okay.
Yes, sir.
All right. So in previous class, we started that is new chapter. First chapter in unit 2. The name of the chapter is Electron Theory of Metals. Electron Students, chapter name is Electron Theory of Metals. So here through this study, we study the behavior of free electrons and properties of solids. Properties of solids. What are the properties like electrical, optical, thermal and magnetic properties. Magnetic. So here the branch which study about the behavior of free electron and properties of solids. What are the properties, students? What are the properties of solid? Tell me.
Electrical, thermal, optical, sir.
And magnetic properties. So based on the free electron behavior, suppose if you take the any solid, inside the solid we have nucleus. Around the nucleus, electrons are revolving in different orbits. sorry, electrons are revolving in different orbits. So the electrons present in outermost orbital are known free electrons. These electrons are the free electrons. The electrons present in outermost orbital is known free electrons. So based on the number of free electrons present in outermost orbital, a very solid behavior is depend. Solid properties are depend based on behavior of free electrons. So to study the behavior of free electrons, our scientists introduced the two theories. Already we discussed in previous class about the two theories. One is the classical free electron theory. Another one is quantum free electron theory, QFET, CFET and QFET. So here, these two theories are introduced to explain the behavior of free electrons in a solid. Through that behavior, we estimate our scientists estimate the both electrical, thermal, optical and magnetic properties of solids. So here, suppose if we take the comparisons and differences between classical free electron theory and quantum free electron theory, students, here electron compared with gas molecule. According to classical free electron theory, it is introduced in the year 1900. It is introduced in the year 1928. This is introduced by the scientist Lorentz and Drude. Lorentz and Drude. So classical free electron theory introduced by the scientist Lorentz and Drude. Quantum free electron theory introduced by the scientist Sommerfeld. So here, according to classical free electron theory, electrons are compared. Electrons are treated as the gas molecule in a vessel. Gas molecule in a vessel or container. So, who introduced the classical free electron theory, students?
Sommerfeld, sir.
Classical free electron theory. Lorentz and Drude. Lorentz and Drude introduced the classical free electron theory in the year 1900. Sommerfeld introduced the quantum free electron theory in the year 1928. But here, according to classical free electron theory, electrons are compared with gas molecule in a vessel or in a container. Here, electrons are compared according to quantum free electron theory. Electrons compared with quantum particle. Compared with quantum particle. That is called fermion. So, next, suppose here another difference, comparison differences between classical free electron theory and quantum free electron theory. Here CFET is the classical free electron theory. Next, QFET is the quantum free electron.
Quantum.
Okay. Wait, ma. Right. So already we discussed 2 points. Classical free electron theory introduced by the scientist Lorentz and Drude in the year 1900. Quantum free electron theory introduced by the scientist Sommerfeld in the year 1928. Here, according to classical free electron theory, electrons behave as the gas molecule in a container. According to quantum free electron theory, electrons are compared as the quantum particle that is known fermion. See the another comparison. Here, according to classical free electron theory, electrons move in a container. Electrons move in a container by following laws of classical mechanics, laws of CM, classical mechanics. Next, Maxwell-Boltzmann statistics, MBS. Next, kinetic theory of gases, KTG. These are all the applied laws in the classical mechanics. So here, it is the third point in classical free electron. Suppose if you take the quantum free electron theory, here quantum particle move by following the laws of quantum mechanics, QM. Next, Fermi-Dirac statistics, FDS. Fermi-Dirac statistics, FDS, and Pauli's exclusive principle. Pauli's exclusive principle. So here, here electrons are compared with quantum particle. That quantum particle behave or move in the solid by following the laws of quantum mechanics, Fermi-Dirac statistics, Pauli's exclusive principle. Pauli's exclusive principle. Already you know Pauli's exclusive principle introduced to explain the electronic configuration in the solids. Next, here through this theory, we study the behavior of electron in the absence of external electric field. That means in the absence of E is equal to 0. Next, in the presence of, that means E is not equal to 0. So we study the behavior of free electron in the metal in the presence of, in the absence E is equal to 0, in the presence of external electric field. So finally we derive the conductivity expression, sigma is equal to n e square tau by m. N e square relaxation time tau by small mass of the electron. Mass of the electron. So here also we derive the same expression. In the place of m, you got the m star. In previous class already we derived this derivation. N e square tau f. Here tau f relaxation, Fermi relaxation type tau f. By m star is the effective mass. So both theories are used to derive the expression for conductivity of free electron in a solid. Next, conductivity of quantum particle in a solid. But classical free electron theory have some drawbacks. To overcome the drawbacks, Sommerfeld introduced the quantum free electron theory. So these are all the main comparisons and differences between classical free electron theory and quantum free electron theory. Students, because already in previous class elaborately about the derivations of the conductivity expression and resistivity expression in both theories. And also we study merits and demerits in previous classes. Today we go to another topic. Students, voice is audible, ma? Hello?
Yes, sir.
Okay. So
Yes, sir.
like from the beginning of the class, we discuss about what are the comparisons and differences between classical free electron theory and quantum free electron theory. Because of classical free electron theory have some drawbacks. To overcome the drawbacks, Sommerfeld introduced quantum free electron theory. These are the basic differences between classical free electron theory and quantum free electron. Today we are moving to another topic in this chapter, that is the origin of energy bands in a solid. What is the topic, ma? Origin of energy bands in a solids. Suppose already you know, if we take the any solid that solid have different energy bands. That means, for example, if we take the carbon, if we take the carbon atom, what is the atomic number for carbon?
6, sir.
Good mark, 6. So because of atomic number of carbon is 6, its electronic configuration write as, see this, what first one, 2 electrons are filled in 1s2. First 2 electrons are filled in 1s2 and form the one completely filled energy E1. And form the one completely filled energy E1. Next, remaining 2 electrons are filled in 2s2. Remaining 2 electrons are filled in 2s2 and form another completely filled energy, that is second energy level E2. Okay. Next, remaining 2 electrons are filled in 2px2. This is partially filled, that is 2px2. In the 2p orbital we have 2px, 2py, 2pz. So this is the 3px, 2px2. Here partially filled energy. This is called valence band because it is made by the outermost electrons. This band is called valence band. These two are the completely filled energy bands. Next, one empty band is there near the 2p, that is 3s2. 3s2. This is empty band because 0, there is no electrons in the 3s. So this is the conduction band. The empty band near to valence band is the conduction band. The partially filled energy band is the valence band. Completely filled energies are discrete energies, E1 and E. So here, if you take any solid, it have different energy bands. What are the separate energy levels, E1 and E2, valence band VB, conduction band CB, and gap between valence band and conduction band. That gap is called forbidden energy gap, FBG, forbidden energy gap. So here, what is the origin to observe these bands in a solid? That is our topic. So what is the topic, students? Please tell me. What is the today's topic? Origin of?
Origin of energy
Energy
bands
band
in
in
Energy band in
solid.
Okay. For example,
Origin of
right.
energy band.
Good mark. If we take the carbon atom have different types of energy bands. How that energy bands are formed in the carbon? That is we discuss now. Suppose for understanding that concept, here I will draw one graph, that is intraatomic spacing versus energy. You take the energy on y-axis. This is the energy. You take the intraatomic spacing on x-axis. Interatomic spacing on x-axis. No problem. Interatomic spacing R on x-axis. Okay. So here, suppose at infinite interatomic spacing, here this is the infinite interatomic spacing. At infinite interatomic spacing, solid have separate energy levels. Suppose in carbon, E1 and E2 energy levels. At infinite interatomic spacing, solid have completely filled energies. Next, if we decrease the interatomic spacing, this decreasing is observed due to intermixing of atoms. Decreasing of R is observed. Decreasing of R means interatomic spacing. R is observed due to intermixing of atoms in a solid. So this is the main reason to form the energy bands. Students, actually, we observe the decreasing in intraatomic spacing are due to intermixing of atoms in solid. Due to that, what happened? This intraatomic spacing R is decreases. At certain intraatomic spacing, these energy bands came to very close. These energy bands came to very close each other and form the band. The set of large number of energy bands is known energy band. Set of large number of energies is known energy band. So at certain interatomic spacing R1, all E1 and E2 energies are come to very close to each other and form the energy band. E1 and E2 are separate energies, isolated energies. Here, but due to this interatomic spacing decrease, what happened? In solid, you observe the bands. That means different separate energies are came to close to each other and form energy band. Next, further decrease the intraatomic spacing. At certain intraatomic spacing or not, at certain intraatomic spacing or not, these two energies are split into two separate energy bands. These two energies are split into two separate energy bands. So this is the splitting. 1 minute. These two energy bands are split into like this, with this gap, forbidden gap. So due to decreasing of intraatomic spacing, what happened, ma? Energy bands are split into filled energy band, partially filled energy band, valence band, empty band as the conduction band. Next, gap between the valence band and conduction band is the forbidden energy gap, FBG. Forbidden energy gap. So like this, we observe the various types of energies. E1 and E2 are the isolated energies are there in solid at a infinite intraatomic spacing. Large number of energies are came to close to each other and form the energy band at R1. Next, these energy bands are again split into valence band and what is that, ma? Valence band and conduction band. These energy bands are again split as this is the valence band and conduction band with some forbidden gap Eg. Some forbidden gap, energy gap Eg. Students, you understand these concepts, ma? Hello?
Yes, sir.
Yes, sir.
So actually, in a solid, you observe three types of energies. Separate energies, that is isolated energies, E1 and E2, energy bands, and due to splitting of bands as valence band, conduction band, forbidden gap. Here we have valence band, conduction band, and forbidden energy gap. Based on this forbidden energy gap, solids are classified into three kinds. What are that, ma? Conductors, semiconductors, insulators. So based on the gap between this valence band and conduction band, we classify the solids into three types: conductor, semiconductor, and insulator. So if in the examination they were asked question like what, write brief note on origin of energy bands in a solid. You explain this diagram. What happened in this diagram that you write as one para, you got complete information. Main reason is due to intermixing of atoms in a solid, intraatomic spacing is decreases. Due to that, at a large intraatomic spacing, separate energy levels E1 and E2 are there. At some less intraatomic spacing, energies are formed the band as a band. At very less intraatomic spacing or not, and these bands are again split into valence band and conduction band with some forbidden gap. Okay, so this is information about the origin of energy bands in a solid. Students, is it understand, ma? Students?
Repeat again, sir.
Yes, sir. Yes, sir.
Okay, ma. Through the material, through the running notes, you try to understand more. Okay. Next, we move to another topic, that is the differences and comparisons between conductor, semiconductor, and insulator. So how we classify the solids into three types based on forbidden energy gap. What is the main reason to classify the solids into three types? Based on the gap between valence band and conduction band. So here, solids or metals. Metals are classified into all of you listen carefully, ma. Classified into three kinds. Three kinds based on forbidden energy gap. Forbidden. Please all of you stop your audios, ma. Students. Ma, Rishi M. Who is the Rishi M? Okay. I'm removing that Rishi M. Here everything is recorded. Who is create nonsense? That student removed from the class. So here solids or metals are classified into three kinds based on forbidden energy gap. Based on forbidden energy gap between valence band. What is that, ma? Valence band and conduction band. Valence band and conduction band. So how we classify the solids into three kinds? Tell me.
Conductors, insulators, semiconductors, sir.
No problem, ma. How? Based on which factor?
Conductor, semiconductor, insulators.
Okay, ma.
Forbidden energy gap. Based on forbidden energy gap.
Forbidden energy gap.
Based on forbidden energy gap. Based on forbidden energy gap, solids are classified into conductor. Next one is semiconductor. Third one is insulator. Insulator. So here now we discuss about the comparisons and differences between conductor, semiconductor and insulator through this table. Okay, so suppose if we take this whiteboard is visible, ma?
Yes, sir.
Yes, sir.
Okay,
Yes,
ma.
sir.
So here in conductors, both conduction band CB and valence band VB overlap to each other. In conductors, conduction band CB and valence band VB overlap to each other. Overlap to each other. Okay. Next, in semiconductors, we have small energy gap between conduction band CB and valence band VB. Valence band VB. We have the small EG. We have, what is that? Small, very less energy gap. Small EG, forbidden energy gap is there. Next, here in insulator, you have the large energy gap between conduction band CB and valence band VB. Valence band VB. So here large EG is there. What is that? Large energy gap is there between valence band and conduction band. Already you know conductors allow the electrons flow completely through it. Semiconductors allow the conduction due to flow of electrons and holes. In insulators, we don't have any charge carriers. Next, here EG is negligible. Energy gap is 0. Here for silicon, energy gap EG is the 1.1 electron volt. Silicon semiconductor
1.1 electron volt.
1.1 electron volt. Please stop your audio.
1.1 electron.
Next, for germanium 0.72. For germanium 0.72 electron volt. EG is the, for germanium EG is the 0.72 electron volt. Next, here EG is very large. That is in the order of 6 electron volt. In the order of 6 electron volt. Next, examples for conductors are all metals. Examples for semiconductor, silicon and germanium. These are element type semiconductors. Indium and phosphorus are the, indium phosphorus semiconductor is compound type semiconductor. Next, wood, plastic, rubber, diamond, all are these insulators. Next, here conductivity is more. Conductivity is in between conductor and insulator. For semiconductors, there is no conductivity in insulator. Here for conductors, by the temperature T, conductivity decreases, resistivity increases. In semiconductors, by the temperature T, conductivity increases, resistivity decreases. There is no effect of temperature on insulator. Okay, here only electrons are charge carriers. Here electrons and holes are charge carriers. In insulator, there is no charge carriers to show conduction. Next, conductors are used to make the electrical wires. Conductors are used to make the electrical wires. In semiconductors are used to prepare the solar panels, to prepare the electronic devices like LED, photodiode. Next, computer switches. All the electronic devices are based on semiconducting technology. Next, insulators are used to protect ourselves from the electrical shocks, electrical shock or electrical that means instability. So from every wire, please ma, every wire have the one outer layer to protect ourselves from the electric shocks. So that is insulating layer. So these are all the some comparisons and differences between conductor, students, between conductor, Sheppandi, tell me.
Semiconductor and
Semiconductor
insulator.
insulator.
Okay, students, today we discuss about two new topics. One is origin of energy bands in a solid. Another one is comparison of comparison differences between conductor, semiconductor and insulator. Okay, so remaining topics discussed in next class ma. In this chapter we have that is classical free electron theory, CFET. What is the first topic ma? Classical free electron theory, CFET. Next, quantum free electron theory, QFET. Quantum free electron theory, QFET. Next, origin of energy bands. What is that? Origin of energy bands in a solid. Next, classification of solids into three kinds based on forbidden energy cap. Based on forbidden. Next, sources in electrical resistance is there. What is another topic, ma? Sources of electrical resistance in a metal. Wait 1 minute. We have 5 minutes time for our class. In that 5 minutes, we are trying to understand the topic, that is sources of electrical resistance in a metal. Very simple topic. All of you trying to understand. Carefully listen, ma. That is topic is sources. Sources of electrical resistance. Sources of electrical resistance in a metals or in a solid. Suppose some conductor shows the resistance when we allow the current through the metals. What is the reason? Students, please stop your audio. Kishore, stop your audio, ma. Sangeeta. Okay, Sangeeta, ma. Hello. Okay, ma, wait, ma. ఎవరైతే నాయిస్ చేస్తారో వాళ్ళని రిమూవ్ చేస్తా ఉన్నాను, మళ్ళీ జాయిన్ కాలేరు. ఓకే, సో హియర్ సోర్సెస్ ఆఫ్ ఎలక్ట్రికల్ రెసిస్టెన్స్ ఇన్ ఎ మెటల్. సపోజ్ ఇఫ్ యు టేక్ ద మెటల్, suppose this is the one metal, copper metal, for example. This is the conductor, already you know. Here copper metal have mass of the copper and electrons charge. Mass is always compared with the positive, electron is the negative. Okay, so here when we allow the current through this copper wire, after flowing some distance, this copper shows some resistance because 4 reasons. That is, one is it have some impurities. Due to impurities present in copper metal. Second one is due to some defects. Next, due to lattice vibrations. Here metal source resistance. These 3 are the sources for electrical resistance in a metal. Suppose this is the copper metal, already you know. Here if it have any aluminum impurity or any silver impurity in it, due to that in this metal we observe some resistance. Next, suppose this metal have some defects. Here some portion is cutting. Due to that, electrons are scattered from the defect from the surface of the metal. Due to that, it shows some resistance. Due to temperature changes, you observe the lattice vibration. That means atoms are vibrated due to temperature changes surrounding the copper metal or any conductor. Due to that, some electrons are scattered. From the surface. So due to temperature changes, we observe lattice vibrations. Due to that, some electrons are missing from metal. Due to defects present in the metal, some electrons are missing. Due to impurities present, resistivity is increases. Due to less purity. So these 3 are the main sources for observing the electrical resistance in a metal. Students, understand this concept, ma? Students, please give reply, ma. Hello.